Hi, I'm Tahmid, currently involved with team subscription. And a bit about me, I'm a software engineer interested on backend, DevOps, and AI. I professionally worked with backend, a bit on frontend, and have been exposed with different technologies like Java, Django, Node, JavaScript, Vue, TypeScript, AWS, and Kubernetes. Client's requirement, huh? So yeah, today I'll be taking on presentation on advanced Java performance optimization, memory management, profiling, and observability. The title is a bit different from what was kind of marketed. I updated the title a few days ago as I thought that reactive programming is a bigger topic and should have its own dedicated session. So yeah, let's start. So the first thing is why this matters. So Java performance and resource directly impacts cost, user experience, system reliability, and developer productivity. Over provisioning will waste money, latency spikes or downtime will affect SLA, give bad user experience. Improper memory configuration can cause downtime as well. And without proper profiling or monitoring, it will be very difficult to troubleshoot. And this will increase cost and delay impact.
Sorry, Tommy, are you sharing?
Yes, hasn't it been shared?
I can't
Yes.
see.
Yes, I can see.
Is it only me? Okay. I'll see it. Okay, thanks. Sorry.
No problem. Okay. So as I was saying that without proper profiling or monitoring, it will be difficult to troubleshoot, causing more cost and delays, impacting business values. So in today's journey, we will see how we can do some memory tuning in containers for JVM. We'll see what will be the best garbage collector to select based on our workload. We will also see some common Kubernetes and cloud issues and discuss about some of the fixes that could be beneficial for us. We will also see how we can do profiling and monitoring in production. And finally, we'll see some observability, tracing, and troubleshooting using OpenTelemetry. So let's begin. So for today's session, I will be mostly focusing on Spring Boot, JVM, and Kubernetes. I will also talk brief about other Java frameworks as well and some runtimes. But I think Spring Boot and JVM, most of us are actually using that. So I tried to focus mostly on these topics or mostly on these technologies. So before we start, just one key takeaway, monitor first, optimize second. We should always measure the impact after we do some optimization in our experimental environment, test environment or staging environment, whatever we have, and then actually deploy to production. Because one optimization could actually hamper another thing. So I grabbed this picture from the internet. There are different kind of pictures and different kind of different kind of definitions of Java memories, but I think this is the most simplest one. So in Java memory, there are mainly two parts: heap area and the non-heap area. In non-heap area, we have the method area, JVM stack, native method stack, PC resource, threads, and things like that. And this is really important when we're actually going to tune the memory. So by default, when we are going to run our application on JVM, it might be not really visible to us, but if we can use some visualization tool, we will see in generally, it also depends based on different runtimes that when the container memory or when we actually configure the container memory to be less than 256 megabyte for Java, we'll see that 50% of the container memory is actually allocated as heap memory. And if it is more than 256 megabyte, we use only 25%. That basically means if we allocate 1 gigabyte memory to your app instance, it will only get 256 megabyte of heap memory. So this is quite important to understand because maybe we need more heap memory and we're just increasing to 1 to 2 gigabyte. But in reality, we will only see that we are getting 512 megabyte allocated for heap memory, and it will make us when we increase them, after we increase the memory, we'll see that why it's not actually increasing that much. It's because how JVM actually works internally. And for different JVM runtime, it could be a bit different. So before you select the JVM runtime, it could be Corretto or Temurin. Basically, the one I wrote here is basically on the OpenJDK or Temurin. So for them, like if you by default, if you haven't done any tuning, it will allocate 25% of the whole container memory, which you actually provided it. So we can actually tune it according to our needs. So there are some tuning parameters that we can use. First one is XMS and XMX. We can specify the initial and maximum heap size of that memory. If you want to put it hard coded, like we want to have 3 gigabyte of initial heap memory and the maximum heap size will be 3 gigabyte, we can use MX and MX. Another way to do it is by specifying the percentage. So we can use max RAM percentage and initial RAM percentage. I find it a bit better to do, bit better because it's more flexible and you can just update the container memory, maybe from the Kubernetes file, or if you're using something else, and it will just automatically update it. There are some other memory tuning parameters as well. There's the XSS stack size. So basically what it does that by default, when a thread is kind of created, it by default it has like 1 megabyte of 1 megabyte memory allocated to it. But if you don't need it, you can actually reduce it. And this stack memory is not actually part of the heap memory, it's actually part of the native memory or the non-heap memory. So if you have more stacks, you might need more non-heap memory. But for virtual stacks, it's a bit if you're using virtual threads, it's a bit different. For virtual threads, the memory is actually allocated on the heap size. So if you're using virtual thread, you might want to have a bit more heap memory than the non-heap memory. Another one is the XX active processor count. So by default, JVM, it tries to read from the node, like how many threads are available, and then tries to calculate the number of processor it needs, and based on the processor, if you're using fork join, common pool, or things like that, it will actually affect the number of threads or the number of threads in the thread pool that will be created. And sometimes it might not be realistic because if you're using cloud environment or Kubernetes where the application actually shared the node. So in that cases, you might want to adjust the count based on your node structure or the node size that you have allocated. So this is a bit real world example, like how we actually define that in Kubernetes. We have these resource limits and request. Request basically means like how much memory and the CPU that the application will need. If it doesn't find this much amount, then it will not schedule your application. It will schedule the application to another node which will actually have that. If none of the node have it, then it won't actually schedule it and shows you some kind of error. And the limit is that if your node has like more memory and CPU after all the application has been scheduled, if it contains more memory and CPU, then it can provide it to your Java application if it requires it. And if you want to tune the JVM parameters, we can use Java ops, this environment variable, or we can actually provide this information directly in runtime or directly when the container is spinning up in Docker file. So we can provide initial RAM percentage, maximum RAM percentage, and all other those memory tuning parameters. Everything actually comes with trade-offs. So we don't want to over provision memory or CPU because it will result in wasted resource, which will actually result in higher cloud cost. We also want to like avoid under provisioning because if you provide less memory, it will increase OM kills because your application will be out of memory. If you provide less CPU, then the CPU will be throttled. That means that your application will get less CPU, so it will take more time to process, and that will increase latency, degrade performance. So my recommendation will be like start with 70% heap of the container memory, monitor metaspace load, and also do some load testing to figure out like if this setting is optimal for you or not. If not, then maybe you want to increase or decrease the heap based on your workload. So every workload will have like a different settings based on how it is used. Maybe some applications like Java applications are like going to have like variable load. So based on that, you might want to adjust it accordingly. And with auto scaling, you also might want to consider auto scaling as well. That is basically like if you at some time, if you're going to have like a peak hour, you want to have like more pods. And to adjust that, you might want to consider like how much CPU you should provide in the request so that the auto scaling can also kick in perfectly. So this actually requires a lot of experimentation in the dev environment, also maybe some experience in the production as well. And the next part I would like to talk about is the garbage collector. Garbage collector is also very important for memory management because based on a garbage collector, the memory will be the memory will be actually divided accordingly. Like for example, if you use G1 GC, and depending on those parameters, the memory will be divided in various sections. Same goes for our garbage collector as well. So there are different types of garbage collector that are available to JVM. Serial garbage collector, parallel garbage collector, G1 GC, GC, and Shenandoah GC. So I won't cover serial GC and parallel GC because unless you have very edge cases, these two are not really that much required. These are like bit old garbage collector. G1 GC, GC, Shenandoah are like newer garbage collector and mostly used in the enterprise applications. So G1 GC or generation first garbage collector as its full meaning. So G1 GC is actually a general purpose garbage collector. By default, it has pause time of 200 milliseconds. That means like if when it's going to do full scale garbage collection, it will actually turn off all those CPU processing that your application does and perform the garbage collection. And it will make it stop for at most 200 milliseconds. It has high throughput. When I say high throughput, it actually means that as it's going to stop everything, it's just doing the garbage collector. And after that, it can after the garbage collection, it will be able to process more requests. And also like as it's going to stop everything, it's going to, from garbage collector perspective, is going to able to collect more garbages or more objects that doesn't have any references. It has low CPU, so the garbage collection actually doesn't take too much CPU. And it is actually a very good choice for small heap size, which is like less than 768 megabytes. This is like my personal preference. When I did experimenting with different garbage collector, I saw that G1 GC actually took very low CPU and also takes very less memory to actually conduct this garbage collector. And when I know in different sources, it says that when you use Java 9 or more than Java 9, by default, it's going to use G1 GC. But in our application, we didn't actually see this because in JVM, the logic is much more complicated. It actually decides which garbage collector to use based on the heap memory that you have provided. And for different runtime, it will be different. For our application, when we used less than 700 megabytes, we saw that it was using, I think, serial or parallel GC. And we had to actually manually force it to use G1 GC. To manually force it to use G1 GC, we actually use parameters, which is -XX colon use G1 GC. There are other parameters you can also tune as well, like the maximum GC pause time, G1 heap region size, how much memory memory size it will create, and if you provide less size, then it will get more memory segments. You can also provide like the parallel GC threads that it will take, initiating heap occupancy percentage. So it's a bit important to understand what this actually means. It means like when the G1 GC will actually start to do your work. So by default, it is 45%. So that means that if your heap occupancy reaches 45%, then this garbage collector will start. So you might want to actually tune this based on your application need. Like if your memory is low, then it might then more GC cycles will appear. Or if you want to have like, if you want to start it like after 60 or 70%, then you can also tune it here as well. Another feature of G1 GC is the use string deduplication. So basically in Java, strings are immutable. And when you create a new string, it will take space on heap memory. If the strings are identical, then what G1 GC can do is like it will only keep one identical string and remove other identical strings. So it will actually reduce your memory consumption. So, but if you don't have any duplicate strings for your workload, then you might not want to use that. There are other parameters as well, but I think the first ones that I mentioned is like more important if you're using G1 GC to reduce memory consumption. Another garbage collector is JGC. So this is a more modern JGC. I think it's now matured on from Java 17 or 21. So it's a hyperscale low latency GC. Hyperscale means that this GC can be used with a very big heap size, up to I think some terabyte, 1 or 2 terabyte heap size. And the main purpose of using GC is like when you require very, very pause time, very, very less pause time when your garbage collector hits. So JGC has very low pause time, which is less than 10 milliseconds. It has medium to high throughput, but it has a bit more, it has a medium CPU overhead as well. That it takes more CPU than G1 GC because of its the way it actually works. And this is actually a good size for medium to large size heaps. So in my experience, what I saw that like if you use GC and your heap size is less than like 768 megabyte, or your total memory size is less than 760 megabyte, then it will cause OM kills because JGC requires some extra memory because of the nature how it works. And there are some default there are some parameters that you can also use to make your application use JGC. You need to use -XSS, use JGC, and the other parameters you can just tune it based on your needs. Another new garbage collector that was introduced by Java is Shenandoah. It's I think in Java 25 it has matured. It is almost similar to JGC. It also has very low pause time. It's still new, so I think in our workload, if you want to consider using JGC or Shenandoah, maybe JGC could be a better choice to go. But it always depends on some experimentation and seeing how your workload actually performs, both on JGC and on Shenandoah, and making the right choice. So my recommendation will be like when you're going to select a garbage collector, if you have a small heap and small latency is not an issue, then go for G1 GC. Otherwise, if you have more larger heap and you require lower latency, go for JGC. JGC is more modern and it has a very low latency, so I think it will be a better choice when you have a lot of memory, when you can actually provide a lot of memory to your application. So next, I'd like to talk about some common Kubernetes or cloud issues that we face often. One is the CPU throttling. So basically in cloud, as I mentioned earlier, like in Kubernetes or any kind of orchestration, we actually provide CPU request and CPU and memory request and limits. If we provide less limit, then it will actually cause throttling, because for JVM and for Spring Boot application, most of the classes are loaded during runtime or when your application is starting, and at that time it actually requires a lot of CPU. With less CPU, it will be throttled and it will take more time to start. So that's one thing. The solution could be like increasing the CPU limit, maybe 2 times more than the actual uses. But main thing is that when we are actually starting the application, it requires, basically what we saw for our use cases or for our client, like basically we need like 100 to 150 millicore CPUs for taking on the load or the request that we have. But during start time, we actually need to have like whole 1 core CPU if you want to ensure that the start time is less than 30 seconds or less than 20 seconds. So it's almost like 10 times the actual uses. So during those cases, we have like other solutions. But in general case, it's better to have like 2 or 3 times the actual use case, 2 or 3 times 2 or 3 times more CPU than the actual uses, so that during start time, you can actually get enough CPU and to reduce the startup time. Another thing is the OM killed. So I think this is something we face in Kubernetes. Initially, we faced a lot. So that's like pod crashes with exit code 137, which is this also includes like total memory, including heap and not heap memory in exceeding the pod memory limit that we actually provided. So to fix this, we need to do some experiments and understand like how much memory that our application needs, and based on it, tune the heap memory or the not heap memory part. And also, if the tuning doesn't help, then we might need to consider increasing memory limit. So the slow cold starts. So what does this basically means? Like the startup time is a log. So during peak time, maybe if you have auto scaling enabled during peak time, we need more application instances to spin up. But if it takes 30 to 60 seconds to spin up, then the extra requests, they can be like timed out, or they can be like cut off, and that will impact user experience. So we want to actually mitigate this. We want to have as less start time as possible, so that the application can take on more requests and application can start up very early and provide low latency here. So there are a lot of different solutions for preventing this. Some of the solution includes, I just provided 3 solutions here. So one thing is the application class data sharing, tiered compilation, and native image. So what is actually application class data sharing? So this actually means that when you're building your application, you will create some shared archive file, and during runtime, you will actually use that file. So this actually reduces the startup time, because during runtime, you're not going to generate all those classes. The ones you were generated during the build time, you will reuse that. So this will actually reduce the class loading time. These are the information I actually got from the internet, but it could be more or less depending on your application setup. So the benefits are that it uses class loading time by some percentage, less meta space uses, and it actually results in faster startup time. It also has some limitations, like you must recreate the archive when your dependency changes, and it doesn't actually affect JIT or framework initializations. It's basically only for the class loading part. Tiered compilation. So JVM uses 2 types of compiler, C1 client and C2 server. C1 client is very fast, but it's not optimized. The C2 one is slow, but it's highly optimized. By default, the JVM actually uses tiered compilation, and it has 5 steps of compilation. The first one runs on interpreted mode, then it compiles to the second one, which is the C1, and then it has 2 more steps where it actually tries to figure out which methods are hot, which methods needs more optimization, and using those information, it uses the C2 one. So as it's like 5 steps, so it takes more time for startup. If we don't need that optimization, then we can actually stop this tiered compilation at level 1. So this will actually reduce start time as well. But if we need, but this actually means like when our application is running for a longer time, it won't actually use the optimized version of the code. It will use less optimized code. So depending on a workload, you might need this, or you may want to avoid this. So you would need to actually experiment with this. So the benefits, as I mentioned, it improves the startup time. The JIT still provides some optimization in C1, so that's good. It's not like totally unoptimized. The trade-off is that you're going to have slightly lower runtime throughput, because it's not going to reach C2 or the level 5 one. And yes, only use this startup if latency matters more than the steady state performance. And the last point I tried to I mentioned, it was the Graal VM native image AIT compilation. So it is still a new technology or new way of initiating your Java application. It doesn't need any JVM. So how it works? It works by performing some static analysis of your code and dependencies. It then pre-initializes those reachable classes and methods and produces a standalone binary. So basically, it just gives you a binary. It doesn't interpret your code. It just compiles and gives you a binary format, which you can run. As it doesn't require any JVM, so it has a lot smaller memory footprint. Its startup is in milliseconds. For JVM, the startup is in seconds, like 10, 20 seconds or more, depending on your size. There is no JIT here, and this is pretty ideal for serverless, autoscaling, or CLI tools. I will also say it's pretty ideal for small workloads as well, where you just creating some small proxies, or your Java application is very small, or it doesn't actually perform that much task. So for those cases, GraalVM is very good. Because I would not suggest for like big applications because of its drawbacks, which is like bigger the application, the longer the build time. Also, it might require extra configuration for reflection and proxies, especially for Spring Boot. You might find it like you had a very long build time, and after you're running it, you'll see that in runtime you're getting some errors there, because it wasn't able to it wasn't able to find those reflection or proxies properly, and it just went with the build. The performance, it says that the performance is a bit slightly slower than the fully warmed GIT, and the debugging and profiling is very, very complex. And especially in development mode, if you want to use a GraalVM in development mode, like you update something and you want to see the changes directly, like a hot reload that we have for JVM. As last time I checked, that's not really possible. So development time is hard. So basically what other devs do is that they actually run the code, they actually develop the code in normal JVM and then just compile it to GraalVM. But sometimes when you compile it to GraalVM, it may or may not work. So this is something, this has some benefits, obviously, and maybe in the future it will be more and more improved. There are many frameworks that actually have like native integration with GraalVM. But for Spring Boot, it's still kind of improving. In Spring Boot 4, they said that it's going to have more support for GraalVM, but let's see. So other common Kubernetes and cloud issues is like having memory leaks, and sometimes we have memory leaks, sometimes we just have misconfigurations of the memory tuning that we did. So memory leak, what is this? So it's basically the memory, your memory is continuously going and going and leading to OM because your garbage collector wasn't able to reclaim the memory. Maybe you had some static declaration, or maybe there's some bug in the code. So how we can identify this? We can identify by using a heap dump and then analyze it with some visualization tools like Eclipse Mat, Visual VM, and JDK. We can also find it with GC logs as well. So in GC logs, we can see like how many times we are getting this full cycle GC and how many memory we are reclaiming. If we see there are some uncertainties with that, or it's not something that we are expecting, then we can see that, okay, there could be a memory leak. So the causes for common leaks are like unclosed resources, static collections, or caching or we are using some like in-memory caching, which we are not actually, which we are not clearing in regular interval. Some listeners or even thread local, where we are just adding some things to the thread local, but not clearing things out. Some of the common fixes includes using try with resources, weak hash map, and remove on thread local. So yes, when you find this kind of a memory leak issue, maybe the better option will be to first increase the memory and then actually do debugging to figure out like what is actually causing this issue. So so in production, to know like how our application is performing, or if we need to do more tuning or not, we need to have CPU and memory profiling in space. So some of the popular profiling methods are Java Flight Recorder, JFR, Java Management Extension, JMX, Spring Boot Actuator, and OpenTelemetry. I will talk more details about OpenTelemetry in a later part. And these are like the profiling methods, but to actually see them, actually to understand them or feel them, we need to have some visualization tools, which are Visual VM, JConsole, JDK Mission Control, and Async Profiler. And these are mostly to use locally. And if you want to have like a production integration and continuous profiling, we can continuous visualization, we can use Prometheus Grafana, or we can also go with Elasticsearch. So this is how a Spring Boot actuator actually looks like. So this is for health endpoint. There are different endpoints as well. And Spring Boot actuator it's very easy to integrate with Spring Boot. Just add one library and some configuration and you're done. And in that endpoint, it provides you a lot of information like this size, which method, some profiling information as well. And you can then actually export that to Prometheus Grafana or Elasticsearch and create some dashboards with that and understand how it's working. Similar goes for JMX as well. So I also wanted to cover how we can actually detect memory leak as well. But I think in our last presentation by Mohibul Bhai and Benjamin Shams Bhai, they actually provided a very good presentation. So I just included a slide and video here. But in addition, I actually wanted to share my experience as well. Like some weeks ago, there was memory leak in an application and how I actually find it out. So I actually used AI to I mean, it doesn't include AI the whole process, but I actually use AI to actually figure it out. So basically what I did was I grabbed the JFR file, provided to the AI agent, and the Claude 4.5, it was able to find out like which code segment was actually causing this problem. So so this was my like steps how I actually performed it. So first I enabled JMX on the application. In Dockerfile, you can easily use some there are some small configurations or some properties you can add, and it will just enable JMX automatically. Then I expose the JMX port on Dockerfile and do Kubernetes deployment, not in ingress and service, because we don't want this to be exposed publicly for security reason. Is just to actually see this locally. Then I use this kubectl to port forward to this port. So our kubectl is not public as well. If you want to get inside the Kubernetes, it triggers SSO authentication, so it's secured. So after I port forwarded the port, then I actually basically have the data in my local host. So I used then Visual VM. I use actually JDK mission control, but you can use Visual VM as well to listen to the port and actually see some live heap, non-heap, CPU threads, and all those other stuffs as well. I also ran some manual GC to see like if it actually makes improvement or not. It didn't make any improvement. I also saw some logs of some ongoing running GC in the tool. After not getting that much information, I started to run JFR to start profiling. I did it for like 1-2 minutes with all those settings enabled. When you actually start JFR, it actually will show you like what are the things that you want to actually enable it. I just did like continuous monitoring and detailed profile, things like that in the JDK mission control. After that, I started to check with JFR, started to see some hot methods or whatever, what objects are actually taking more memory. So it was showing jar by things like that. I also tried to check from the stack trace. Didn't get much information to that. But I think if I look deeper, maybe I could have figured it out. But then I just feed it to the AI. I also opened a project application that was actually having this memory leak, and the AI used that as a context and also use JFR file, and it actually figured out like which part of the code is actually causing this problem. And after I fixed it, I found that yes, that was actually causing the problem. It also gave me the details like why it was actually causing that problem, and I actually find it reliable. I had a good experience with Claude Sonnet 4.5. And if your experience after tuning those memory parameters, if your experience is still no good, you can go with GraalVM, which is a native VMS compiler. You might also want to consider other frameworks as well, like Micronaut, Quarkus, or even Spring Reactive. If still doesn't work, maybe a different framework like Go or Rust. So this might be difficult to develop because it doesn't have that much community support, or it doesn't have like that much, what do you say, like a lot of good articles on it, but it can actually solve your problem. And recently I also saw this Kubernetes CPU startup boost. So in Kubernetes, you have uh, this feature where you can start up where you can actually boost your CPU for some time, and this will actually decrease your startup time. You can actually mention like how much time you want this CPU to be boosted. After that, it will reduce to the normal request CPU limit. So this can also help you. So the next part is the observability. I want to talk about OpenTelemetry here. So why do we need this? In observability, there are three pillars: metrics, logs, and traces. Metrics means what is happening. Logs gives us information about why did it happen, and traces show us how the request actually flows. In distributed tracing, there are three concepts, which is trace, span, and context propagation. Trace means like end-to-end journey of a request, how the request is actually flowing from your multiple applications. Span is the single operation within a trace, and context propagation is mean like, let's say you have multiple services. You have microservices, one application communicates with another microservice that communicates with another microservice. How one request is actually flowing through those services. To know the information, we use trace IDs. And to propagate this trace IDs, it's the context propagation. So what is actually OpenTelemetry? OpenTelemetry is an open source framework standardizing how we collect and export telemetry data. This is vendor neutral. This is not dependent on any program. It has a lot of it has APIs and SDKs for most of the popular programming languages, and you can use that to instrument your applications and capture data. It has standardized protocol, and it has an optional component called ODL collector. So there you can actually receive, you want to actually export to the various backends like Elasticsearch, or in AWS, I think in AWS it's called X-Ray. And for different cloud service, there are going to be like different backends you want to export and see the result there. So these are, I just grabbed some of the pictures or features that the OpenTelemetry has. We are also using this for our clients as well. So this is the service map visualization. It actually shows you like how the services are like interconnected with each other. So we can see here that front-end RAM is communicates with front-end node, and that actually communicates with different backends. We can also see the request flow here as well, like how this is a request flow of 3 services. For each we can see that this request flow for one request, like start from summary service, then goes to customer service, and then communicates with transaction service, and how much time it actually taking. And with this, we can actually analyze and figure out like what service is taking more time, or wherever most of the latencies lie. And in Kibana logs, like I mean, most of us, we actually export logs to a log collector and then visualize with some things like Kibana or CloudWatch. If we don't have trace IDs, then there are a bunch of different logs that kind of exporting, and we can't actually correlate the logs. Like we can't actually see what logs actually a particular request generated. So it becomes difficult to understand like why a certain request fails. But we can easily solve it with trace ID. What OpenTelemetry does that when a request comes in, it actually includes a trace ID if there is no existing trace ID, and it just propagates to all those requests that are actually sent from that particular service. So I just grabbed this from our Kibana, and I know my editing is a bit bad, but I just wanted to give you the overview of like how it works. So here I just did some filtering with trace ID, and I can see how request has been propagated from app1 to app2. And using this, I can actually see like where, if a request fails, then which part of the request actually caused the issue, or what actually took the most time. And we can also create dashboards and alerts with those data that we exported, the trace data or matrix data or the logs data that we exposed. And using that, we can create dashboards. So this is the dashboard of the memory uses of an application. We can create other dashboards as well, like how many port was kind of up in a certain interval, how many 5x's count that we got in a certain interval, latency, 2x's count, or anything. Basically, we can just create dashboard in any data that we have. And integrating OpenTelemetry with in our JVM or Spring Boot is pretty easy. So if we go with Java agent, it has actually support for JVM directly. We can just use the OpenTelemetry Java agent. So this is like my suggestion, or the way we are actually doing it. We can just create a directory, OpenTelemetry, where we can put the latest OpenTelemetry jar. I provided the link here as well. Optionally, we can put the OpenTelemetry sampler jar as well. So we can, there we can actually configure which traces we want to export and which trace we don't want to export for, because trace takes a lot of spaces. So we just want to export the traces that we want. And then the configuration file. In the configuration file, we actually say different information like the name of the service, traces we want to export, where we want to export, things like that. So it's not showing everything, but just to give you a fact that this is like the configuration file that we can use. And it's a big configuration file, but we don't need to actually update everything here. Just service name is the most important part here. And in our Docker file, we can just use the Java agent one. We need to just specify where our OpenTelemetry Java agent is, the configuration file, and if you have extensions like the OpenTelemetry sampler or something or more, we can just provide it here, and automatically it will start exporting the traces. No need to update the application code. If you want to have specific spans based on your method or specific part of the code, then you need to include the library and include some annotations there to create those custom made spans. Otherwise, this Java agent will take care of everything, like database spans. If you have integration with events or RabbitMQ, those spans, or any external HTTP, because all those spans will be taken care of by the agent. So in production, there are some best practices that we can follow. We can use sampling, that we just want to have 1% of the request to be transported to our backend, because traces, it contains a lot of data and it actually contains a lot of spaces. So in production, generally, we don't want to for 100%, but if your application is small and 100% and you have a lot of space in your backend, or the cost isn't a matter, you can export one-hand tracing. More trace you export, maybe it's easier to actually debug it. Another best practice could be like trace only the critical paths that actually can cause the issue. Keep your span lightweight. That means only adding the important attributes that you need, not actually adding all those attributes. And retain data smartly, like keep traces for 5-7 days or 3-4 days, because traces are mostly to give information about how your application is performing, or how application is kind of communicating with other services. You can also use it to get insight of your application or insight of your system. You have logs to actually debug your application, so you might not need 100% tracing, or you might not need to keep traces for like more than 7 days, but it depends on your workload and also your operations as well. And to optimize performance for the tracing, generally OpenTelemetry has a very low CPU overhead. I think the internal is less than 1%, but if you have a lot of tracing, or if you have a lot of data coming to your production application, then it can increase the CPU overhead. So to keep the latency impact minimal, you can do sampling. Proper sampling includes what I mentioned about like 1% of the request should only be exported, or only trace some critical paths, things like that. And now we are actually end of our presentation. So here are some of the best practices or the suggestions that I have. It can be different based on your application requirement or your operations. So the first point is like using the latest stable Java frameworks and libraries, gain performance to gain the best performance possible, and also for having the best garbage collector and security improvements. Also adopt virtual threads if you're using Java version 21 or higher for high concurrency and structure. And also if you're using Java 25, you can also use structured concurrency as well, which is the new feature for Java 25, and I think it's actually have a lot of hype. But we should use virtual threading mostly if we have like IO heavy workloads. If your workload is like more CPU bounded, then maybe virtual thread won't be much helpful here. And also use small base images like Eclipse, Xamarin, Alpine, or distroless Java, or even you can use binary like native images. This keeps the container size minimal, so it has less surface area for attack. So it's like a bit more secure. And in production images, you include only JRE, not JDK. So because JRE, it only includes the runtime environment. JDK, it includes different build tools as well. So it has a bit more surface to cause an attack or if someone got access to your environment, it can gain more data with those tools. So it's better to keep the production images as small as possible. And tune the JVM parameters based on profiling and load tests, and doing some more experimentations. Other best practices like enable GC and thread monitoring. Basically, you want to get more information about your workload in production, and also tune those in your test environment to see like how much improvement you get. Perform realistic load testing. Always have alerts and dashboard for continuous monitoring, and if anything goes wrong, you should be alerted, and you can just, before the client actually complains, you can actually go with the fixes before the client complains. So it gives you like it's like a better way of going forward. And other parts are like warm up critical endpoints, enabling string deduplication and compressed ops for lower memory footprint. And I think the other ones, they are like mostly conventional that we try to follow. Sometimes we're not able to do it because of other priorities, but it's better if we can actually follow this. So that concludes my presentation. So if you have any questions or feedback, please free to ask. Anyone?
Any questions, everyone?
No question. Just want to say I think it was a very good presentation. Thanks, Tamid.
Thank you, Tom.
Thank you so much, Tahmid bhai. And
I would like to appreciate the use of AI regarding the JFR. I couldn't think it up. Like I can do that. It didn't come up to my mind. That was a very great way of using AI, I guess. So I learned it today. Thank you so much for that.
No problem.